Hello and welcome to the final demonstration for Group 28's project SignFlex. The SignFlex team consists of two computer engineers and two electrical engineers, Antonius, Ryan, Madison, and Esteban. The objective of the SignFlex project is a technical solution for the disconnect between those who speak American Sign Language and those who do not. Our team is looking to bridge the communication gap between the two groups utilizing modern technology. Our solution is a wearable glove that accurately recognizes and translates the American Sign Language alphabet and provides the user real-time translation and feedback using a mobile application. For our system overview, we have three main portions of our glove. In the wristband, we have our PCB storage. Our PCB houses our accelerometer, our battery monitoring system, and our regulators, as well as the connections for the flex sensors. In the opposing pouch, the batteries are stored on the opposite side, consisting of two lithium-ion batteries. The PCB then has JST connectors that wrap around the wristband with the wires, as you can see in the photos, and connects to the 5 flex sensors, one for each finger. And now we will take a look at our custom PCBs. For the SignFlex team's PCBs, the team ordered 2 regulators and 1 main PCB. For our main PCB, it consists of 4 layers and has the following: micro GST connectors for flex sensors, a USB-A connection for uploading data to the ESP32, an ESP32, our fuel gauge and battery monitoring system, as well as our accelerometer for measuring tilt and hand orientation. And pictured on the right-hand side of the screen is our 3.3-volt regulator for our accelerometer, fuel gauge system, and ESP32, as well as our 5-volt regulator for our flex sensors.
Hi, my name is Madison, and we're going to be looking at the 3.3-volt regulator today from Group 28's project SignFlex. As you can see on the breadboard, we have our 3.3-volt regulator, and we have our connections as follows. We have our input from our simulated 5-volt regulator, our 2 ground connections, and our very left-hand output of 3.3 volts. Today we're going to be using a programmable electronic load to simulate that our 3.3-volt regulator is functional. And we have our DC power supply here that will demonstrate and act as the 5-volt regulator. So if I power this on, we'll be giving our 3.3-volt regulator 5 volts. And as you can see on the electronic load, as well as the board, the LED has lit up, signaling that the board is on, and we're receiving 3.3 volts, as well as you can see it on the multimeter. And now we're going to give this board some current. I set, and we're going to try 0.05, enter, and we're going to turn it on. And as you can see, we dipped just a little bit with 0.047 amps and 3.29 volts. If I use my multimeter, and see, we're still receiving 3.3 volts. Now I'm going to try 0.5 volt, or 0.5 amps, excuse me. As you can see, we are getting 3.12 volts and 0.496 amps. If I test with my multimeter, I'm still receiving 3.3 volts. And now we'll try with 1 amp, which is the maximum current that we can use for our regulator. As you can see, we've dipped down to 2.46, 2.47-ish with our resistance, as well as 0.996 amps. And if I test with my multimeter, we're looking at about 2.8, which is expected due to the fact that 1 amp is the maximum that we can put on our regulator.
Good afternoon. This is Group 28. I am Esteban Rios. We are the SignFlex Glove project, and right now we are going to test our 5-volt regulator. So as you see here on the breadboard, we have the 5-volt regulator hooked up to both the power supply and also the DC electronic load. The voltage input that the regulator will be receiving will be 7.4 volts in order to recreate what it would be receiving on the main power source, since we have 2 lithium-ion batteries that are connected in series, equaling out to 7.4 volts because both are 3.7. And we are going to measure the output of the regulator as well as test the output when we increase the current in the electronic load. So right now we're going to set this up and show you the results. right now we're going to measure the output of the 5-volt regulator from the board. So if you look here in the ohm meter, we are getting 5 volts. Now, we're going to test the output when we change the current on the load. So we have 5 volts here, so on, and then I set, right now we're going to test 0.001 amps. And of course, since there wasn't really a change in the current, it's gonna be 5 volts. We're gonna increment it to 0.5. So when we increase the current to 0.5, we see that our voltage output drops to like 4.8. We can still measure again the output of the regulator. When we do that, we are getting again 4.9 volts, around 5 volts. And now we're going to test the electronic load again, but now we're going to try with 1 amp. So when we have a load that has an output current of 1 amp, as we see here, our voltage output drops to 4.6.
So now I'm going to walk you through the computer vision aspect of our project. This was a key part of our system that allowed us to classify American Sign Language letters using hand gestures in real time. So we started by training our ASL classifier using a custom dataset of hand gesture images. The graphs here show the training and validation performance were over 25 epochs. As you can see, the model quickly reached almost 100% training accuracy, and the validation accuracy settled around 92%, which is showing that our model learned the gesture well and generalized it very good. The loss curves confirmed that with our loss training dropping sharply and validation loss showing a bit of variability, which is typical for our ASL model. Overall, the results were strong and indicates that our model was ready for real-time use. And once the model was trained, we deployed it in our Android app and we tested it with our SignFlex glove. And as you can see in these pictures, the results of the letter A and the letter B, the system consistently predicted them correctly, with response times around 20 to 27 milliseconds and accuracy between 91% and 99%, which matches our requirements for this project. This showed that our model wasn't just good in training, but also performed very well and reliably when used in live with our glove. This slide explains how accuracy is measured in SignFlex. Our model gives a confidence score between 0 and 1 for every predicted letter. We multiply that score by 100 to get a percentage, which we show as an accuracy on the screen. To make prediction more reliable, we wait until the same letter is detected constantly across 10 frames before displaying it or speaking it. And as shown in the screenshot on the right, the real-time displays includes predicted letter and the system response time in millisecond and also the confidence based on accuracy percentage. This helps the users knows both the system is recognizing and how confident it is in real time.
In this scenario, we'll be demonstrating the computer vision.
A, B, C, D, F, D, F, L, Y, Q, N, M, W, X, R, V, L, V, T, A, B, C, D E F G H R I K D L B M N D B O P Q R F R M S T V T V W X Y.
Now we're going to show the mobile app. This is our dual mode ASL recognition system, also known as our mobile app interface. We have 4 screenshots showing certain features of the app. If you go to the left side, our first screenshot is our login and authentication. You can see that we have the you can log in with the username and password, but the picture I have showing is the registration feature where you can obviously register for an account. And if you go to screen 2, you can see the profile button, and you can go back to change your username and password and other features you like to change. If we go to screen 2, you can see it's our intuitive navigation with our clear action buttons, showing all the other features of the app, where you can do the direct connection to the ESP32 and all other features featuring Bluetooth. Also with our camera ASL, glove sensors, and dual mode, and it gives back real-time letter prediction display with visual feedback. If we go to our right side, with the screenshot number 3, you can show our dual ASL recognition, which takes the Tony computer vision and our flex sensor output and fuses the data to give one correct output. We have it where thresholds of 80+% accuracy, so it doesn't constantly spit out random data, so we can make sure it's always giving something accurate and reliable data. And it gives you feedback such as waiting for accurate signal for low confidence detections. If you go to screen 4, we go back to the main screen, and you can see the comprehensive glove sensor reading display featuring the battery monitor and the flex sensor angle measurements for all 5 fingers that it's getting from the ESP32. Also with real-time metrics tracking. Yeah, so overall, the SignFlex mobile app provides comprehensive ASL recognition solution with camera-based and hardware-based app. When you first open the app, it will take you to the login screen. Since we're a new user, we'll click on the register screen on the bottom. Let's do test at example.com, test 1 2 3, and test 1 2 3. Once you register, we'll take you to the home screen, and if we close the app and reopen it, we'll still be logged in. Once you're taken to the home screen, if you scan for the glove, you'll be connected to the ESP32 as its name for our ASL glove, so it won't connect to any other ESP32. As you can see, in real time, the flex sensor data will change as you bend the glove back and forth. From here, you can go to the camera ASL, which can detect a letter. Since we're not doing any letter, it won't be detected anything, as the accuracy shows. And from here, you can go to your profile if you want to see. That's the username and email we put in. You can update your profile and change your password as you like. And from here, you can go to our the flex sensor data output, where you can see the serial monitor and real-time data output between each raw sensor data from the flex sensors for each finger, along with the battery percentage. If you go to, let's connect back to the ESP32. If you go to the dual ASL, this is where our combined recognition kicks in. Since we have no accurate data, because we have a threshold of 85%, the combined recognition won't put out an output until it reaches that 85% threshold. The camera will think what it detects, but the accuracy is not accurate, so it won't spit it out. And the same with the flex sensor.
For this portion, we will have a project demonstration highlighting our engineering specifications.
And now we'll be demonstrating our moving letter, which is J and Z. So we start with J.
J.
Following up our second movement letter, which is Z.
Z.
In this scenario, we'll be demonstrating static letters
A. B. C. E. G. P.
Thank you for watching our demo.